Hi everyone! In this video, I'm going to show you meta solving techniques. Basically, they allow you to get the answers to the problem without actually solving it. And I know, of course, you should be trying to actually solve the problem first, but if you're running low on time or you don't know how to do the problem, these are a great way to get some extra points on the AMC 1012. So basically, the first technique is known as engineer's induction. Basically, what this means is that you try small values, small numbers in sequence, and then you try to notice a pattern, see what is emerging. And sometimes you don't even have to try numbers. You can just try one number and it will work. So let's look at this problem here. It's a great example of engineering induction. So we have this long sequence. A1 is 1, A2 is 3 7, and this complicated expression here for all n is greater than or equal to 3. And you want to find A 2019. Okay. So this may seem impossible, right? We have this weird expression, and then we have to find 2019 terms of line. So there's no way you can just bash it out. So you might be overwhelmed here at this point, being like, I don't even know what to do here. So the idea here is 2019 is a huge number. So instead of looking for 2019, let's just try to find one or two terms, see where it goes maybe. So we know A1 is 1. So if A1 is 1, let me just write that. So since A1 is 1 and A2 is 3 sevenths, we know that A3 is going to be equal to A1. So A3 minus 2 is A1 times A2 divided by 2 times A1 minus A2. And A1 we know is 1. A2 is 3 sevenths. So then we divide this by 2 times A, so 2 minus 3 sevenths, which is just going to be equal to 3 sevenths by 11 sevenths, which is 3 over 11. Okay? Now let's try finding A4. A4 will be equal to, A4 is just going to be AN minus 2, so 3 sevenths times 3 elevenths over 2 times 3 sevenths minus 3 elevenths, which is just going to be equal to 9 over 77 over, it's going to be equal to 6 sevenths, so 2 times 3 sevenths is 6 sevenths, which is also equal to 66 over 77 minus 21 over 77, which is just going to be equal to 9 over 45, which simplifies to 3 over 15. So we know A1 is 1, A2 is 3 7th, A3 is 3 11th, A4 is 3 15th. So you're probably already noticing something here. Look, so the denominators are always increasing by 4. So the denominator of A2 is going to be 3 over 7. Denominator of A3 is 3 over 7 plus 4, so 3 over 11. Denominator of A4 is 3 over 15, so 11 plus 4. So it looks like each time the numerator is always being 3, and the denominator is increasing by 4. And we can also notice that A1 is equal to 3 over 3, so A1 also satisfies the pattern. So basically, for any n, A of n, this is our guess based on the small values we tried. So A of n is just going to be equal to 3 divided by 3 plus however many times n minus 1 times 4. Because basically, an is just going to be equal to, by our pattern logic, the denominator is just going to be 3 in the beginning, and then for each term we go to the next term, we're adding 4 to the denominator. So in general, an is going to be 3 over 3 plus n minus 1 times 4. So that means A of 2019 is just going to be equal to, this is going to be 3 over 3 plus 4 times 2018, since, remember, you can think of it as a 2019 turned into arithmetic sequence with first term 3 and common difference 4, which is equal to 3 over, and this is just going to be equal to 8,075. So then we add the numerator denominator to get 8,078, which is the answer. So the idea behind this problem is that rather than just being scared by this complicated notation, we just took a few examples and we noticed a pattern. That is exactly the process of engineering induction. So this is very powerful, useful not only at the AMC 10-12 level, useful at the AMY level too. So definitely a really good technique to have handy with you. Okay, now let's look at the next problem. How many 15-letter arrangements of 5 A's, 5 B's, and 5 C's have no A's in the first 5 letters, no B's in the next 5 letters, no C's in the last 5 letters? So remember, if you remember watching or attending the combinatorics class, remember we actually solved this problem using actual combinatorics. But now I'm going to show you, the kind of the cheap way to get the answer to this problem without actually doing it yourself. Because if you're short on time or you don't know how to do it, this is a pretty tricky problem. And here's the technique that can help: engineering induction. So rather than looking at it for 5 A's, 5 B's, and 5 C's, and no A's in the first 5, no B's in the second 5, no C's in the last 5, why not just make it 1? okay, so instead of saying first 5 letters A's, let's just make it so that the problem is no A's in the first slot, no A's in the first letter, no B's in the second letter, and no C's in the third letter. Okay? So now let's just look at all the possibilities. So basically, you have to have no A's in the third, and then something like this is something that could work. So now we just have to list all the possibilities and see which ones work. So the permutations of ABC, ACB, I'm just writing out all the permutations, and I'll cross out the ones that don't work. So these are all the permutations of ABC. And you can see that the ones that don't work are the ones with A's in the first letter. So A cannot be the first letter. Or the ones with B's in the second letter. Or the one with C in the third letter. So we see that there's really only 2 possibilities left. So therefore we see that if instead the problem said, instead of 15 letter arrangements, 1A, 1B, 1C, instead we have 3 letter arrangements, 1A, 1B, 1C, then the answer would be 2. So now looking back at our answer choices here, we have these long numbers in terms of 15 and 5. So basically, in order to find what the same corresponding thing would be for, instead of 15 total letters and 5 of each kind, let's make it 3 total letters and 1 of each of the kinds. So if you kind of replace 15, if you replace this 5 with the 1, replace all the 5s with the 1, and replace all the 15s with 3s, since now there's only 3 total letters. Now we can see that if this problem was now in terms of just one letter instead of 5, these would be the option choices. So now all we have to do is check which one of these 5 option choices is equal to 2. Well, this first option choice is essentially the summation of k equals 0 to 1 of 1 choose k cubed, which is just equal to 1 choose 0 cubed plus 1 choose 1 cubed, which is equal to 1 plus 1 equals 2. Oh wow, that's equal to 2. So now we know that A is a potential candidate for the answer. But just to make sure we're not missing anything, let's just make sure the other 4 choices are not equal to 2. So B is just going to be 3 to the 1 times 2 to the 1, which is 6. So B doesn't work. C is just going to be 2 cubed, or 8, which also doesn't work. This next one is going to be 3 factorial over 1 factorial cubed, which is just going to be equal to 6, which also doesn't work. This last one is going to be 27, which doesn't work. So see that A is the only one that has a corresponding value equal to 2. Okay, so now what? Well, now let's take a look at the possibilities. So we can clearly see that A is the answer. And this technique, like I said earlier, is not only working for this value. We can see that we don't even have to try multiple. Just try one. We see that, okay, A is the only one equal to 2. And that's it. No need for any complicated combinatorics. Just look at the small case and generalize by pattern. So that's literally what engineering induction is all about. And it's very powerful. So definitely make sure to keep an eye on this for the AMC 10 this year and 12. Okay, so now let's explore another meta-solving property. Basically, find the unique properties of numbers. And I'll actually talk about these techniques later because I think it's best illustrated by an example. So we have this large equilateral triangle constructed by some rows of toothpicks. So in this figure here, they say we have 3 of these rows, and we have a total of 5 triangles at the bottom here. And now, so they're saying now instead of 3, we want to have 2003 small triangles on the bottom. Now we're asked to find how many total toothpicks. So if there's 2003 triangles on the bottom, then we can see that there's always going to be one more upward facing triangle than downward facing triangle. So you can think of these blue triangles here. There's always going to be one more of these blue triangles than of these green triangles. So there's always going to be one more upward facing triangle than downward facing triangle. The reason is that if you think about pairing them up, there's always going to be one extra upward facing triangle. So out of these total of 2003 triangles on the bottom, we're going to see that there's going to be 1002 upward facing triangles and 1001 downward facing triangles, right? Okay, so now what? Now what we can see is that, well, now how many total toothpicks are there going to be? So now the total number of toothpicks we can see, well, notice that the total number of toothpicks, think about all these triangles individually. Think about each of these triangles here. So each of these triangles consists of 3 toothpicks, right? So now each of these triangles that I'm just marking here, if you extend it to 1002, it's from 3 on the base to 1002, we can see that there will be a total of 1002 times 1003 divided by 2 equilateral triangles, and each of those triangles has three toothpicks in it. So we multiply by 3. So now one way to evaluate this is just to multiply the whole thing out and see which option choices matches. Or a more clever way is to see that, like I was mentioning the techniques here, look for the unique properties of numbers or option choices. Rather than calculating it out, think about just the unit digit. So if we look at just the unit digit, it's just going to be 2 times 3 divided by 2 times 3. So if we look at just the unit digit, it's going to be 2 times 3 by 2 times 3, which is just going to be 9. Okay, so if the unit digit is 9, which one of these option choices has the unit digit of 9? The only option choice with the unit digit of 9 is C. So we know that that has to be the answer. So rather than evaluating 1002 times 1003 and possibly screwing up there, just look at the unit digit, because that's a unique defining property of the number. Like, now let's discuss these techniques that I had, a long list. So you can look at the unique defining properties of numbers, of the option choices that we have. So in this case, in this example here, we saw, okay, the unit digit is a unique property. There's a different unique digit for all the option choices. So sometimes you might see that, okay, this option choice is the only one that's maybe 0 mod 3, leaves a remainder of 0 and divided by 3. So you can do the same thing for unit digit, last 2 digits, parity, like whether it's odd or even, square, whether it's a perfect square or not a perfect square, prime number, composite number, modulus, denominators of common fractions, and many more. So it's not limited to these. So in general, just look for the unique defining properties, and also, like we'll explore soon, you can look for the choice that's the odd one out. Okay, so now let's take a look at the next technique. So this technique, basically, you look for the choices that are different from all the other ones. So we have this equilateral triangle. We extend AB beyond B, and so to the point BBC. So we have this equilateral triangle ABC, and we're extending the points AB along side to beyond B to point B prime. So we're extending to this point B prime, such that B prime times B is 3 times AB. So AB, if the equilateral triangle has side length x, basically you can see that B prime will have a length of 3x, right? And that we can also see that if we extend AC beyond a point, it says in the problem here that extends CA beyond the point A to point A prime here, we have the same thing, and C prime here too. So no matter what, we have these lengths are always going to be 3x, 3x. Okay, so now we have our diagram set up. Now we need to find the ratio of A prime, B prime, C prime, the big one, to the small one. How can we do that? Well, without actually solving the problem, this is somewhat of a trick you can use. So I'm just going to erase the letters just to clean it up. The total side length is just going to be 4x here. So the total side length here is 4x. The total side length is 4x, right? Because each of the parts are x and 3x, right? So the total side length is 4x here and 3x there. Then we can see that A prime, C prime is just going to have a length of, we can actually just use the law of cosines in this case, if you know what that is. Or if you didn't know what the law of cosines was, a trick you can see is that if something has side lengths 3x, 4x in a right triangle, it's a Pythagorean triple, then this hypotenuse has to be 5x. If that's in a right triangle, of course. But that's not always the case. Sometimes we might have an obtuse triangle like that. And if it's not an obtuse triangle, we can see the hypotenuse is going to be bigger than 5x, right? Because it's obtuse, we're thinking of stretching it outward. So a right triangle has 3x, 4x, 5x. An obtuse triangle will have hypotenuse bigger than 5x. Intuitively, that should seem true. So that means that this side length is going to be greater than 5x. Okay? So now what? Well, now we can, by the equilateral triangle area formula, the area of ABC is just going to be equal to square root 3 by 4x squared, right? And we can also see that, okay, ABC is area of square root 3 by 4x squared. What is the area of A prime, B prime, C prime? The area of A prime, B prime, C prime is going to be, is going to be 5 times bigger. The side length is 5 times bigger, more than 5 times bigger. So the overall area will be more than 25 times bigger that of the smaller equilateral triangle. Because the side length is more than 5 times bigger, area is proportional to the amount squared. We didn't even need to do all this business equilateral triangle area. So from here we can see that these 3 choices are all ruled out, right? Because we see that it's going to be more than 25 times the area. So now we're just left with 2 choices. So now what can we do? So now we can see that, just like the technique says, look for the choices that are different from all others. So from 9 to 1, 16 to 1, 25 to 1, 36 to 1, 37 to 1. So out of 36 to 1, 37 to 1, which one is different from all the other ones? Well, it should be clear to hear that 36, 25, 16, 9 are all square. So 37 is the one that's different. And that's why we see that that's going to be the answer to this problem. Okay, so the next technique we're going to learn about is trying all the option choices. So in this problem, we have Alice, Bob, and Carl playing a game. They each choose a number between 0 and 1. And Alice announces, oh, I'm going to choose a number between 0 and 1. Bob says he's going to choose a number between 1/2 and 2/3. And we want to find what number Carol should choose to maximize her chance of winning or getting in between Alice's and Bob's number. So let's just write it down. A is 0 to 1. B is 1/2 to 2/3. So we want to find a value of C that will maximize the chance of winning. So the idea for this problem is A will have an expected number 1/2. B's expected number is just going to be 3/6 plus 4/6 divided by 2, or 7/12. So we can see that C's number will have to be in between A's and B's expected number. So we can see that the expected what number Carol should choose has to be in between 1/2 and 7/12. So we can see that all of these option choices are not in between 1/2 and 7/12. So 13/24 is the only option choice that's in between 1/2 and 7/12. Therefore, picking this number is the only choice that will maximize the chances of winning because it's in between the expected value of Alice's number and Bob's number. So therefore, 13/24 is the answer to this problem. Okay, so now let's move on to a really clever application of GCD. So basically, if you remember from the number theory class, we discussed how to actually solve this problem. Now let's explore the meta-solving way to do this. So we have some numbers such that GCD A and B is 24, GCD B, C is 36, and CD is 54. And we have the special condition that the GCD of A and B is between 70 and 100. So notice that A has to be a multiple of 24, of course, right? It hopefully should be clear. The A has to be a multiple of 24. And then we can see that D has to be a multiple of 54. Right? So that means GCD A and D, the GCD of numbers A and D, has to be a multiple of 6. So if A is a multiple of 24, if D is a multiple of 54, GCD of them is a multiple of 6, right? Okay, so if GCD A and D is a multiple of 6, that means the possible values for GCD A and B between 70 and 100 is 72, 78, 84, 90, and 96. So these are the only possible values. And in order to have a factor that must be a divisor of A, if a divisor must be a divisor of A, it has to also divide GCD A and D. Because otherwise, there won't necessarily be need for it to be a divisor of A. So we can see that one of these primes has to be a divisor of GCD A and D. So we can just see that, okay, out of all these values, 72 to 96, which one of them has any of these factors? So you can see that 78 is the only number from 72 to 96 that has any other factor other than 2 and 3, since 78 is 6 times 13. So you can see that GCD of A and D will have to be a multiple of 13. Okay? Because the reason is that GCD of A and D is a multiple of 78. Since this is the only one of the option choices that matches any of these conditions that will be a factor of any of these values from 72 to 96. So there's another clever application of the technique of how we can just narrow in on the answer choices and see that 13 is the only one that's a factor of any of the possibilities for GCD A and D. Okay, so now let's move on to the next problem. So now we're going to move on to a similar technique, elimination of choices. So this is where you eliminate choices and you narrow it down to 1 or 2 maybe, so you can guess. So this problem, we want to find the least possible value of x plus 1, x plus 2, times x plus 3, times x plus 4, plus 2019, where x is a real number. Okay, so what do we do? Notice here, well, the idea for this problem is that we can see that the largest possible value of this number. Let's just take a few examples. So clearly you can see that x plus 1 times x plus 2 times x plus 3 times x plus 4 is just going to be an integer, right? So not necessarily an integer, but it can be 0. Because if you plug in x equals 1, x equals negative 2, all the way till x equals negative 4, we can see that the expression is 0. So now what? So we can see that 2019 is definitely possible. So the 2019 is definitely possible. We just let x equals negative 1 or negative 2 or whatever, right? So now is 2018 possible is a real question to be asked here. Is 2018 possible? Well, we can actually notice that x plus 1 times x plus 2 times x plus 3 times x plus 4 can be negative, right? Because if you plug in something like x equals negative 1.5, this will give us a negative value. Because if you plug in x equals negative 1.5, we get that this is equal to negative 0.5 times 0.5 times 1.5 times 2.5, which is clearly a negative number. So clearly you can see that something less than 2019 is also possible. So the least can no longer be 2019, because something less than 2019 is also possible. So now we're limited to just two choices. So now what can we do? So now the idea is now, the real question, is it 2017 or 2019? So now we can just try a few more values maybe. We can try negative x equals negative 1.1, x equals negative 1.3, x equals negative 1.7. And you'll see that always you're not getting below 2018 ever. You're always a little bit above 2018. So from here we can see that it's pretty likely that the answer is 2018. Because if you're never even getting below 2018, the answer is probably not going to be -1 below 2018 or 2017. So we can see 2018 is the answer here. And we eliminated 4 option choices. We see that the second one has to be the correct answer. This is another powerful application of the elimination of choices technique. So you can eliminate all the ones that you know won't work and leave the ones that you know will work. Now let's take a look at this problem. Which of the following is the value of log 2/6 plus log 3/6, the square root of that? Okay, so the solution for this problem is to approximate, or not the solution, but the way to estimate the answer is to approximate these two quantities. So we can see that the log 2 of 6 is going to be about 2.5, right? Because the log base 2, because 2 to the power of 2.5 is going to be about equal to 6. So now what? Well, now, if the log base 2 of 6 is about 2.5, what is log base 3 of 6? We can see that 3 to the power of 1 is 3, 3 to the power of 2 is 9, so it's going to be like in between those two values. So we can see that 3 to the power of 1.5 is also going to be about 6, meaning that log base 2 of 6 is about 2.5, and log base 3 of 6 is about 1.5, right? By logarithms property. Meaning that the square root of this is going to be about 2.5 plus 1.5, which is going to be about 2, right? So you can completely eliminate these two choices since they're below 2, they're much below 2. And we can see that, well, the values that are going to actually result in this working, we can also see that it's not going to be exactly equal to 2 either. So we can cross that out. Since we can see that the value is going to be greater in log 2/6 plus log 2/3 is going to be actually greater than 2. So now it's left to these two choices, D and E. Well, notice that when you take the square root of the sum of two numbers, it's always going to be less than the sum of the square roots of numbers. The reason is that, let's take an example. The square root of 16 plus 9 is 5. The square root of 16 plus the square root of 9 is 4 plus 3 is 7. So intuitively, this should seem true to you. Because when you take a square root of a big number, you're making it very small. But when you take the square root of smaller numbers, they're not becoming as much smaller each. So we can see that log 2, this quantity is always going to be greater than this quantity. So we can cross this out. So now we just have D. Log 2, 3 plus log 3, 2. Okay? Because now we just have this final choice here. So we can see that this is the only one that should work. So we see that this is probably the answer for this problem. Okay, so now let's take a look at our next problem. Next type of problems. So we have the square ABCD with side length 30. And we have these P such that AP is 12, BP is 26. And we have these centroids of all these different triangles and the vertices of our quadrilateral. So just notice that the centroid of the first triangle, APD, is always going to be 2/3 of the way from the point. So it's going to be roughly here, right? And the same thing with this bottom triangle here. The centroid is going to be approximately here. Because remember the property, the centroid is always 2/3 of the way from the point. So these are the 2 points, these are the 2 centroid points, right? Okay, so these are the 2 centroid points. We can see roughly that it's going to make up 2/3 of the overall side length of the square. Because the side length of the square is 30, then this distance here is going to be about 2/3 of that, so about 20, right? And doing something similar for the other side, we get that the diagonal here is also going to be about 20. So you can see that really the area of this thing is going to be about a square with diagonal 20. That's going to be approximately the area of of this region. It's going to be about a square root diagonal 20. So then a square root diagonal 20 is just going to have a total area of 20 times 20 divided by 2, which is going to be equal to 200. And we can see that that's actually the answer for this problem. So really clever technique of estimating rather than doing a coordinate bash, which I would presume to be the easiest way to do this without it. So the reason from there is that the way to do this is just to guess it and see that, okay, 2/3 of the way, and then we can see easy finish from there. So meta solving is just not completely, you still have to apply some logic, some intuition, some properties of geometry, but it simplifies your work greatly. And rather than coordinate bashing or doing something like that, you just have an easy way to see that it's going to be 200. Okay, now let's take a look at the next problem. So this problem is from the AMC 8, 2 years ago. So basically we have this triangle with A equals 2, A1, E equals 2, and then we have these parallel lines. So like we have these two lines that are parallel. So the idea for this problem is that we can actually estimate the areas. So the ratio of the area of CDEF to ABC, well, how can we do that? The reason is that look at the areas approximately. What are the areas really? Well, so we can intuitively see that the area of CDEF, this area in the middle here, is going to be less than the sum of areas ADE and EFB. So you clearly see that the area of the two triangles is greater than the area of the rhombus in the middle. It seems pretty clear from here in the diagram that they have. And even though they say diagrams are not drawn to scale, they generally are. So don't worry too much about that. So what is the ratio of the area of CDEF to ABC? Well, how can we do that? We clearly saw that the area of CDEF is less than the area of the two triangles. So we know that the answer has to be less than 1/2. So we can eliminate these option choices. And we can see that the answer has to be equal to A, 4/9, because we can see that all other 4 option choices are 1/2 or more. A is the only choice less than 1/2. And we clearly saw that the rhombus is way smaller than the area of the two triangles. So it's a powerful application of estimating in geometry. Now let's move on to the last technique, and this is probably one of the most powerful ones, and it's actually been known to trivialize some very late AME problems too. So basically, we have this binary operation diamond that says that A diamond something, some equation in terms of diamond. Okay, interesting. And then we have A diamond A is 1. Okay? So now what? Well, and then we have to find the solution to this long equation. So what do we know here? We know that A diamond A equals 1. That seems strangely familiar to division, because A divided by A is also 1. So maybe the diamond sign is just division, right? So this lets us be maybe it's division. But then if it's division, does it satisfy this property, the second property here? That's the next question we're going to ask. If it's division, will it satisfy this property? Well, the answer is that if it's division, let's say divided. Let's check if it works. This is just going to be A over B over C equal to A over B times C, right? So is this true? Well, we can see that it actually is true, since this is just equal to A times C over B, which is equal to this quantity here. So we can see that this is true, meaning that division does satisfy both their properties of A diamond A1 and A diamond, this long equation, is true. So you can see that if diamond is division, then we're done. So we can actually assume that diamond is just going to be division. We can assume diamond is just division. So we can just say, okay, this is going to be 2016 divided by 6 over x equals 100. And then we can easily solve that 2016 over 100 equal to 6 over x. And then this gives us an easy finish that x is just going to be equal to 100 over 2016 times 6. And then we can simplify our terms here. So we can just do 2016 divided by 6. And we can see that 2016 divided by 6 is just equal to 300 and 2016 divided by 6 is 336. So x is just going to be 100 divided by 336, which is equal to 50 divided by 168, which is 25 over 84. So you can see that the answer is just going to be equal to 109, because we want to find the sum of 25 and 84. So the answer is 109. And the fraction is 25 over 84. Okay, so the idea, this might be a little bit confusing, that how can you just assume it's division? The idea is when you're giving freedom in certain parts of problems, just assume it's true. So basically, if you're not knowing that, we're not knowing that it's not division. So the problem never states anywhere that it can't be division. and division does work. We can just assume it's division. Another classic example of this is that, so basically the idea is that since it satisfies A diamond A is 1 and this second condition here, and division does satisfy it, then we can just assume it's division. Another classic example of this is that if we have, let's say, a triangle, and then we're given that some triangle, and you have to do some property of this triangle. Some property of this triangle, you calculate some ratio. So a common way to use this trick to those kinds of problems, just to assume the triangle is equilateral or something around those lines. So you can assume the triangle is equilateral, and then it makes the problem a whole lot simpler from there. And a classic example, so this type of technique always generalizes, so you can always just say, oh, I don't know anything. I don't know. No one's telling me that this triangle is not equilateral. So I can just assume it's equilateral. And then if it's whatever ratio I get for equilateral triangle, it will hold true for all triangles. This type of technique is very, very powerful. Because now here's a summary of all the techniques we covered today. In linear induction, we tried small numbers and found a pattern. Looking at the unique properties of numbers, so we can just calculate like the unit digit or the parity and see that it's the only one that's odd or something like that. Or we can look for the choices that are different from all the other ones and see that, okay, this is all different, so it's probably not going to be any of the ones that are all the same. You can estimate the answer in geometry or non-geometry problems. You can eliminate choices and leave one or two choices to guess or get the right answer from. And lastly, the most important one is when you're given freedom in parts of the problem, just assume a certain thing is true, and then it makes your problem a whole lot simpler. So in total, these techniques are very useful for getting the answer to the problems, but I highly encourage you to actually try to solve the problem first, and not just try to use these before you even try solving it. This should only be used as a backup if you don't know how to solve it or you're running short on time, but nevertheless, these can be very useful and can definitely raise your score by several points. Thank you all for watching this video, and if you enjoyed it, be sure to also like and subscribe to this video.